Good morning, everybody. Welcome. My name's Ron Hackney. I'm not Sarah Kasevich, who unfortunately has come down with COVID. So I'm stepping in at the last minute to be your MC today. I'm a little bit unprepared, but we'll see how we go. And I'm losing my voice already. So welcome. I'd like to acknowledge that we're meeting today on the lands of the Ngunnawal and Ngambri people, which is the home to the Acton campus. I acknowledge that First Nations people carry a lot of knowledge. And as a scientist myself, as a Western type scientist, I acknowledge that we've got a lot to learn from the First Nations peoples in terms of their knowledge systems. And it's really pleasing to be here today, and we're going to hear about lots of great science on the country, the land of the Ngunnawal and Ngambri peoples. Without too much further ado, I'm going to hand over to the Director of the Research School of Earth Sciences, Louis Moresi, who's going to give us a quick welcome. So over to you, Louis.
Okay. Thank you, Ron. Morning, everyone. Welcome to the Research School of Earth Sciences. I'm Louis Moresi, and I'd just love to welcome you here today to our seminar room. It's a little small and it's a little grubby, but it's been the home for 50 years of our seminars, and we're pretty proud of it, actually. So this promises to be a very fascinating conversation about Antarctica today, and I'm looking forward to it. I would also like to acknowledge the Ngunnawal and Ngambri people, custodians of the land where we meet today, and I would like to celebrate their elders, past, present, and those who are emerging. And I would also like to thank our co-hosts for making this event possible: the Embassy of Italy in Australia, the ANU Institute for Climate, Energy and Disaster Solutions, the Centre for Public Awareness of Science, Geoscience Australia, and the IODP Italia. And I'd like to also welcome Dr. Marco Lazzarino, who's the scientific attaché of the Embassy of Italy in Australia, and will help with the introductions and running of the event today. So thank you all for being here, and thank you for the Embassy's support in bringing this together. I would also like to acknowledge Sarah Kasevich and Ron, but actually Sarah, because she did actually most of the work here. She brought all of this together. And the Ron and Sarah manage the International Scientific Drilling Program for Australia and New Zealand, and they do that here at ANU. So I'm sorry, Sarah, you're probably online listening. I'm sorry you can't be actually with us today, but we're very grateful, and we're thinking of you, wish you a speedy recovery. I just wanted to spend 1 minute to say, well, why Antarctica and why Italy and Antarctica together? So RSES has incredibly deep roots in Antarctic science. I would like to acknowledge that one of our former directors of the school, Professor Kurt Lambeck, pioneered our understanding of how changes in ice sheet loading influences the Earth's topography, and with that changes sea level. And that's work that remains today foundational in this field, and is part of the work that we do. Our researchers study the dynamics of the Southern Ocean. They study the history locked in Antarctic ice cores, mass balance of ice sheets measured from space, and the seismology of the continent beneath the ice. RSES-led teams have deployed rapid access ice drills in East Antarctica, and our scientists have published landmark work on how Antarctic meltwater is slowing the deep ocean, overturning circulation. And this has profound implications for the climate system. Our former colleague, Professor Neroli Abram, who led much of the Antarctic work here, is now Chief Scientist of the Australian Antarctic Division, and this tells you something about the work that we do here. All right. But no one can do Antarctic science by themselves. No individual, no nation, and no single country can do anything like this work on their own. So there's the Italian connection, which runs deeper than many people do realize. Italy has been a major Antarctic nation for many decades, and operates research stations and contributes to some of the most ambitious drilling and survey programs on the continent. And here we have many links to Italian earth science and Italian Antarctic research in particular. But we have many Italian trained researchers on our staff. We have many publications and collaborations with colleagues at Italian universities, And we recently signed an MOU with Italy's INGV for the geophysical connection. And in doing so, we formalized a collaboration that's been growing for many, many years. So today's seminar, of course, is itself a product of those long-standing collaborations. A long-standing connection with OGS in Trieste and with Dr. De Santis too. So the scientific drilling programs that we run here connect us, and they are also a wonderful example of international collaboration. So today's event is at the exact intersection of two things that this school cares about very deeply: understanding Antarctica and scientific research that crosses international borders. So I would like to hand over to Marco to take over and talk a little bit more about the Italian connection to the school. Welcome.
Thank you. Thank you, Luis, for the nice words you spent for the Italian connection, which sometimes sounds quite a scary Italian connection, but in this case, it's a good one. So I'm Marco Lazzarino. I'm the science attaché at the Italian Embassy, Embassy of Italy in Canberra. Basically, my job would be that of facilitating the connections and the cooperation between our two countries. I should say that in Antarctica, I mean, I'm definitely useless. I mean, there are already enough collaboration. I can't put anything more than what is already existing. But yes, I think there are still things to be done. So I'm really happy to be here, really happy to be organizing this event together with the help of the Research School of Earth Science, together with the help of the Institute of Climate, Energy and Disaster Solution. And actually, thanks very much to Sarah and Kate to organize for these two institutions this event. And also the Australian National Centre for Public Awareness of Science and Geoscience Australia, who are will be present here and in the panel later on. So why we are interested in Antarctica? Because as Luis said correctly before, Antarctica is the best example of international collaboration in science. And this is also well defined by the Antarctic Treaty System that designates Antarctica as a place for peaceful collaboration and scientific discovery. So no other, not different activities rather than science and peaceful collaboration. And as Luis correctly mentioned before, Antarctica has a situation logistically, the size of Antarctica, the distance from the other countries, for the other inhabited places and the conditions that requires a common effort between different nations. So that's why Italy is there, because we want to participate to this global effort, the worldwide effort. Italy joined the Antarctic Treaty in 1985, while Australia, I think, was one of the first one to sign the Antarctic Treaty. And right after the signature of the treaty, we established our first base in Antarctica, the Mario Zucchelli station that was established at the Ross Seashore in 1986. And now we are working and operating in Antarctica since nearly 40 years. A little bit later, I think in the 90s, no, I don't remember the name, the year, we also established together with France one of the only three bays which are permanently used in the continental area of the Antarctica, the Concordia Station at the Dome Sea. The others, if I'm not wrong, are the Amundsen Scott from the US and the Vostok from Russia. And also Italy operates a fully equipped research icebreaker, the Laura Bassi, that Laura knows very well, because I think you spent many, many months on the Laura Bassi, probably. Only 2 months. Okay, they're more than enough. For me, more than enough. And last year, we also hosted the annual meeting on the Antarctic Treaty in Milan, and you probably were there. So we are still committed to operate Antarctica as a peaceful environment. And as we will learn today from Laura and from the panel, free and peaceful access to Antarctica is essential. It's more and more essential to understand many aspects of our planet. And for example, what we are listening today will be how to expect and how to adapt to the climate change and the threats that this effect is posing to humanity. So I'm really anxious to listen to Laura's presentation and to the panel discussion, as I imagine all of you are. So I will stop here and let the stage to the real scientists. Thank you very much.
All right, I guess we come now to the main event. So welcome, Laura. It's great to have you in Canberra. Thank you for taking the time to come down to join us here. Laura's just come off, not so long ago, off the RV Investigator, our research ship, which was doing some science off the Cook Glacier in Antarctica. So I'll quickly introduce Laura. I have caught myself out a little bit here. Went, oh my goodness, I didn't get the bio, but I have it here now. So you've probably all read it, but I'll highlight a few things. You've seen that she's a senior researcher at the Istituto Nazionale di Oceanografia e di Geofisica Sperimentale, OGS in Trieste in Italy, with my best Italian. She's an internationally recognized leader in Antarctic marine geoscience, looking at seismic data, bathymetric data, so geophysical data, combining that with the sediment cores that we can get from below the seafloor in these big international programs that we've been a part of. And it's still a part of. She spent a lot of time at sea, so not just 2 months at a base, but 300 days at sea. How do you feel about that, Marco? And importantly, cold, yeah. And she was a co-chief on an international ocean discovery program, Expedition 374, to the Antarctic margin. That was 10 years or so ago, I think, right? 2018, yeah. Which was quite a major expedition that's really changed some of our thinking in that region. So she's a member of the IODP Science Evaluation Panel and has held many leadership and advisory roles across the European and international polar research initiatives. And I won't go into more. Like I said, I'm sure you've read the bio already. We'd really like to hear from Laura, so let's focus on the time on hearing about your science. So Laura, thank you very much for coming by and welcome. Yeah.
Can you hear me well? Okay, so I think I'm not going to use the microphone, but in case, just let me know, because my voice is quite low. First of all, let me thank all of you to invite me here. It's really a pleasure and honor to be here with you, and I hope you find this interesting, but my main purpose is to discuss with you after, to have a panel discussion and to meet everyone who is interested to go a bit more deeper into this topic. I'll just start with the.
We have to click in the window first. Sorry? I'll try. Yeah.
Yes. Thank you. Yeah, just a couple of slides with some basics about cryosphere for those who are probably not so much familiar with this. And this is showing how the two poles behave, basically, where most of the ice is localized. So the Arctic is basically an ocean. It's covered by sea ice, which is changing significantly during the summer and winter. And there is only a relatively low ice sheet, which is based on Greenland, while the Antarctica is a continent, basically is mainly a continent covered by a thick ice sheet, and it's the sea ice is also shrinking during the summer, but in some regions is a kind of perennial and it never disappears. In terms of size, we know that the ice sheets are the major component of the cryosphere. They are very thick, they are very much extended, and they take millennia to create, to form, and may take a shorter time to shrink, to melt, but they are the biggest component of the cryosphere. While the glaciers, which are the one that we are more familiar with, they are also in the low latitude. They're much, much smaller, and their lifespan is much shorter, and the sea ice, as I said, is seasonal, and so we have different kind of component of the cryosphere that behave in a different way, but they're all interconnected. So the ice sheets, in terms of size, they are but very much different. So the Greenland ice sheet is much smaller. So the equivalent sea level rise globally is about 7 meters, and it's melting very fast, much faster than Antarctica, about 0.76 meters per year. While Antarctica is what's so-called a sleeping giant, because it is a giant. It contains an equivalent of 58 meters of global sea level rise, but apparently is more stable than Greenland. Only a relatively narrow region is losing ice mass, which is the region in the western side. I don't know if you see the mouse remotely, but basically the western side of Antarctica is the one with the orange region, which is where the ice mass changes is very much accelerated during the most recent years, and it's losing mass at 0.43 millimeters per year. The ice mass has been much bigger in the past. During the last glacial maximum, there was much more ice on both the north and the south, especially in the north, where the ice sheet was much bigger than Greenland. It was covering most of North America and Northern Europe. And since then has been melting. So in 20,000 years, basically there was a loss of 130 meters of equivalent global sea level rise, which happened in stepwise, as we see from the Great Barrier Coral Reef. We did see that basically what's happening is that the ice sheet has been melting fast initially, and then much slower. And then there were a couple of stepwise meltwater pulse, like the one happening in 340 years with plus 20 meters of global sea level rise. I can use this splatter here. Doesn't work. So there was a big meltwater pulse of 20 meters of global sea level rise in only 340 years, around 15,000 years ago. And that may happen again, because there are still at least 22 meters of global sea level rise equivalent stored into the Antarctic most vulnerable region that could be melting if with the ongoing global warming. But we don't know actually how fast and when this will happen. So one of the scientific challenge for our community is to understand better what the mechanism actually driving the sensitivity of the remaining Antarctic and Arctic ice sheets. This is because we have predictions. So in the next 300 or 2,000 years, we know that the CO2 concentration in the atmosphere will be rising. We have more optimistic and less optimistic predictions. We probably will be facing the less optimistic predictions, which is where with the CO2 concentration in the atmosphere of more than 500 ppm, which means a global average temperature rising 4.4 degrees centigrade, which will be probably bringing us in a world similar to what was in the Miocene many years, 23 million years ago, when the global sea level rise was 30 meters above the present day one. And so one of the things that we try to look at is to learn from the past what happened during that time, how our planet looked like, and how much ice was on land, and how fast we can go back to this kind of situation. Through different steps, like across the last interglacial, 1,100 to 2,800 years ago, 1.2 million years ago in the marine isotope stage 31st, or in the mid-Pliocene when we had this warm Pliocene climatic optimum about 3 million years ago. So all of these steps can teach us, can show us how much ice was sitting on the two ice on the polar regions, particularly in Antarctica, because that's the largest one, that's the thickest one, which is the one that was driving actually the sea level when the Greenland ice sheet was not developed yet in the very warm and high CO2 world in the Miocene. There are predictions about how much ice will be remaining in a very warm global planet. So those models, for example, this one in the upper left is predicting melting of the whole West Antarctica, in this case, but also part of East Antarctica, like in this region here and in this region here, with less optimistic scenario. And that was based on a few observations from few regions obtained by a drilling program and also by some land outcrops. But the models are very coarse, they are not very well constrained by enough data, and that's why we do have such a large uncertainties, especially for the long range. So in 2300, the prediction of global sea level rise fluctuate between around 2 meters and more than 5 meters. And these uncertainties is due to the poor knowledge about the actual paleoclimatic record. So we need more records to refine this kind of model and predictions. And one of the uncertainties is linked to the role of the ice shelf. The ice shelves are those termination of the ice sheet at the end of the ice sheet, which is the shelf which is floating, and it's buttressing the ice sheet ice flow, preventing the ice sheet to be melted by the ocean warming. And so the ice shelf has a critical role in actually stabilize the ice sheet itself, because once the ice shelf is melting and disappearing, then the ice sheet is exposed to the ocean, and most of the case it's running back, is basically accelerating, disintegrating and accelerating backwards due to this landward slipping subglacial bedrock, which is much deeper into the interior of the ice sheet than in the outer shelf, because of the deep erosion due to the ice sheet advance and retreat multiple times across the continental margin, and because of the ice sheet low. So once the ice shelf disappear, then the ice sheet increase their flow seaward and thinning and then collapsing. So understanding what's the status of the ice shelf surrounding and bordering, protecting the Antarctic ice sheet is one of the main issues of the scientific community at the moment. It's particularly true for West Antarctica because, as I said, this is the one that is losing mass more than other parts of Antarctica, which are quite stable. But it's also important in East Antarctica because there seems to be a connection between where you have the highest ice mass loss and the subglacial topography. By comparing these two figures, we do see that when we have the highest ice mass change, we do have also the deepest subglacial topography, which is the blue regions here is where the ice sheet is basically grounding on the seabed. So it's the actual base of the ice sheet is below the sea level. And so it's particularly vulnerable to ocean warming and and sea level rising. While the area where the ice sheet is not presently losing mass, but actually potentially gaining mass, is in East Antarctica, in those regions where the ice sheet is sitting on land, on the continental land. So it's less vulnerable, less exposed to ocean warming. In this region where the ice sheet is not losing ice mass, is because the ice shelf are still protecting the ice to be attacked by the ocean, which is this region here in the Weddell Sea and this region here in the Ross Sea. In fact, in this case, the temperature of the bottom water is very warm. It's warm. It's about 0 in this region here, where we don't have ice shelf. So the glaciers are exposed directly to the warming ocean, and it's still blue, so it's still cold. It's below 0 in the Weddell and the Ross Sea, and also in most of the region around the East Antarctica, apart from these two cases here, where the ice sheet is a marine-based ice sheet, and with no ice shelf. So the IODP expedition between 2010, 2018, 2019 were particularly interested to get some more observations in those regions where the ice mass change is higher, and those regions which coincide with the marine-based ice sheet, so where the ice sheet is sitting on seabeds rather than on the continent. So it's more vulnerable. It's the first ice sheet that will be disappearing in the next future. Sorry. And where we can have we can obtain observations about how the ice shelf and ice sheet interact with the circumpolar deep water, which is the water which is the main component of the Southern Ocean, and it's generally above 0 degrees. So it's a warm current, which when find the way to get to the continental shelf, tend to melt the ice shelf from beneath, and then cause the thinning of the ice shelf, and then loss of ice sheet buttressing. So that was one of the targets of our expedition in 2018, that Rob Mackay from Victoria University, New Zealand, myself, and Denis Kulainet from Texas A&M in the US. We were leading this expedition in the Ross Sea, and that was an incredible voyage with 13 nations represented. And now we have a much larger shore-based team working on the data and the results. It was a great voyage with many scientists, half of which were women, so good balance between the genders and lots of technical and staff and students. There were many students and career scientists, so there was a very nice and interesting experience. And we were main interest to look at the interaction between the ice sheet and the ocean. So just to give you an idea about how the Ross Sea look like today from an oceanographic point of view. We do have circumpolar deep water, which is the water, the warm water coming from the ocean with more than 1 degree centigrade, bringing some heat inside the Ross Sea. across the continental shelf and reaching the actual Rosside shelf, melting the actual Rosside shelf at the front. So we do have some orange color here showing that the actual melting of the Rosside shelf happens due to the incursion of circumpolar water in the Ross Sea. But the circumpolar deep water, which is a modified circumpolar deep water, doesn't get too far because if we look at this section in the upper part here, which is this red track line, is a bit articulate, but it's close to the grounding line. It's close where the ice is detaching from the bed. We don't see any evidence of circumpolar deep water, even the modified circumpolar deep water. It's all very cold ice salinity shelf water, which is the one below zero, and ice salinity shelf water and ice shelf water. They are both below zero. They are salty, a little bit fresher, this blue one here, but they are quite salty, and so the Rosside shelf somehow is still not melting so much, apart from the frontal region and this little corner here. So it is protecting still the ice sheet to disappear, to disintegrate. So the circumpolar deep water is not so effective in the Ross Sea yet. But in the past, when the ice sheet is actually advancing all over to the continental shelf edge, up to the point where it would not actually go beyond, because that's the ocean, so it's kind of start to float. At that time, maybe the circumpolar deep water was indeed a factor triggering the ice sheet retreat. So that was the motivation why we did put our drilling sites right at the front of these boundaries between the ice sheet, maximum expansion, and the ocean, particularly along this conduit, which is a canyon, the Hillary Canyon, which is one of the main routes for the circumpolar deep water to go in, and one of the main routes for the Ross Sea bottom water, the ice salinity shelf water forming in the Polinia, to go out. So this is a key gateway where we do have ocean current exchange nowadays, but also in the past. So it's a good point where we can investigate what was the relationship between the ice sheet stability and its ice shelf and the ocean, the warming ocean, back in time, in the past, during super interglacial, super warming interglacials. And this is, for example, the site 1523, which is located on the edge of this bank, the eastern bank, which is too deep to ever been carved by the ice sheet. The ice sheet was never able to reach this point, but was quite close. And so these sediments, these very thick stratified sediments here, they were deposited during in ice proximal to ice distal location. And they also have a very good record of ocean current, because they have this typical sigmoidal shape, which is typical of sediment drift, because where the sediments pinching here, you have a very thin and condensed sedimentary section is where the current is strong, preventing the deposition of sediment. But here, where the sigmoidal feature is thickening, is where you have a very expanded section, a very high expanded and stratified section, which is where the current is slowing down and allowing the sediments to deposit. So we have from high expanded to low expanded section, from high resolution to low resolution, but older section to investigate, and in an ice proximal to ice distal condition. And then we also have this site 1524 in the deeper part of the margin along this Hillary Canyon here, intersecting both the circumpolar deep water going in and the Ross Sea bottom water going out. On this side of the canyon, on this levee, 1524 is receiving the sediment from the continent, so the glacial material that has been dropped at the edge and then flowing downslope and spinning up over these this levee and deposited in 1524. So we have the ice distal to ice proximal record and the very distal glacial marine record of the current. And just to decipher a bit, to understand a bit how the different sedimentary phases can be observed in a drill core like those, I give you just some information about how they look like. So in a very proximal region, very close to what we call grounding zone wedge, which is a wedge forming at the base of the ice sheet, right at the front, when the ice sheet starts to float. Here, the grounding zone is this point here. The sediments forming here, they are what we call glacial and ice proximal. So they are diamic tight. And they look like this. So they are basically made by a matrix of mud, silt and clay, but also sand with clasts. So all sort of grain size. No stratification, only in this region here. We do have some stratification due to the position along Forsyth's bed and the sorting of the material along slope. And in a relatively ice distal position, we may have this kind of sediment here, which is the gray one. It's basically mud because it's much far from it's far from the grounding zone. At the grounding zone, the coarse material is deposited. A little bit farther, you have finer and finer material. So it's the matrix is much finer, but we do have ice-rafted debris flow, ice-rafted debris, which are these clasts which are dropped by icebergs on the seafloor and entrained into the mud. And in a very distal situation, like near the margin here, the continental shelf, we have mainly diatom-rich sediments, because in open water with no sea ice, no icebergs, no coarse material, we mainly have only this laminated greenish algae, which is this yellow kind of So if we look at the drill sites, 1523 on the bank, the one I showed you before, compared with the undrilled site that was drilled before in a very proximal corner of Ross Sea, very close to the ocean shelf, we do see some potential correlation in terms of times. Of course, the 1523 is away from the grounding zone, even when the ice sheet was expanding, never ground over 1523. So what we have is only these light green ice proximal to ice distal sediment. And we do have a few layers of diatoms interlayered between these glacial ice proximal to ice distal sediment. So the 1523 is recording a very high expanded and high resolution section, which can be compared to the 101 section. And it's quite consistent. During the same glacial times, we do have glaciers also in the inner Ross Sea. And when we have the deposition of this diatom algae yellow bases in both sides, we do have a consistency period of global warming. So that means that there is a coincidence between superglacial warming, when the circumpolar deep water was interacting with the ice sheet, triggering the ice sheet to force its retreat up to the undrilled 1 deep. So it did have a role, at least during the retreat of the ice sheet from this point to this point, several times during this time frame. If we look at the 1524 in the deeper part of the margin here, we do have also a very nice record, which is basically overlapping the same record, which is the Pleistocene. In this case, we do have gravity flow and turbidity flow cascading processes triggered by cold dense bottom current, bringing diatoms in the deep water. And basically that's how the core look like. So we have a stratified turbidity layer, which are basically diatom, rich diatom ooze material. So by correlating with the three drill sites, we do have evidence that during the Pliocene superinterglacial interval, which is between 2.6 and 3.3 million years, the global temperature was 4 to 5 degrees warmer than today. And in Antarctica, there was much less ice cover, and also the Antarctic bottom water was much, much less intense. We can detect this from, for example, foraminifera, because we did find the subtropical and temperate planktonic foraminifera, particularly in the super warm MIS marine isotope stage KN3 at 3.16 million years. And we have a gap in turbidity record, so there were not turbidity current during this time. So the production of Antarctic bottom water was much less. After the mid-Pleistocene transition, the climate was cooling, and there were less and less the planktonic fauna was showing a much stronger bottom current, but the temperature was less. The sea ice developed more. And so the water current were more corrosive, and there was a kind of polynya environment, much better developed, which is also protecting the continent, the Ross Ice Shelf. So it's acting as a role of stabilization for the ice sheet. So I'll skip this because I don't have time. I'll just show you another example from the Miocene, which is this site in the middle of the continental shelf. We are now in the Miocene climatic optimum, where the continental shelf looked like much different from today. So there was an embayment in the middle of the Ross Sea. 1521 is right in the middle of this embayment, and we detected a very high expanded section of this Miocene climatic optimum. At this time, the concentration, the CO2 concentration in the atmosphere were much higher, analog to what we can find in the next 300 years. And the Ross Sea was completely free, no sea ice, no Ross Ice Shelf. There were incursion of the Kumpola deep water. There were no clasts, so the ice sheet was very much far. And there are mollusks, so we could detect also the temperature was incredibly warm and with no ice. And another thing I want to show you very quickly is the role of this yellow diatom algae-rich layer has in the margin. So we also discovered that each of these very thick layers correlate with seismic reflectors, which can be then traced to the margin, and they are actually weak layer of a gigantic submarine landslide, which affects the Ross Sea, and it's connected apparently to super warm interglacials when the ice sheet retreat and the continental margin isostatically rebound. And so create the condition for slope instability and basically favoring the development of this giant landslide. A similar thing has been observed in the continental margin of the Cook, in this region here, where legacy data shows there are also in this case evidence of a large landslide, but we don't know the age of it, we don't know the size of it, and what was the trigger of it. So that was the motivation for a survey that we did in 2022 with Laura Bassi, founded by the Italian Antarctic program. And that was followed by the voyage that we just had this year, with founded by IMAS and the Antarctic Research Council, led by Linda Albrecht from IMAS. So what we did, we wanted to date these large avalanches. We wanted also to go on the continental shelf, but there was too much sea ice, so we couldn't get there. So we focused on the continental ice, and we did get very nice sediment cores at the head of this landslide, and we probably know much more about what was the causes. Yeah, so this was just a photo to show you the team of this voyage. I know that some of them are perhaps online, and I really want to thank Linda and all the team, because that is another amazing expedition, and I really enjoyed to be on board, and that was great. We collect very, very nice data, so you will hear more about this in the near future.
Thank you so much, Laura. It really demonstrates the benefits of bringing the different data sets to get the geophysical data, getting those sediment samples, and informing how we do the modelling and predicting what's maybe going to happen in the future. So yeah, thank you very much for that. And yeah, we really look forward to seeing some results from this survey as well when it starts to come up. Okay.
Yes.
Okay. There's some sneak preview highlights for it. So the plan now is we're going to switch to a little panel discussion. Then there'll be an opportunity from questions from all of you in the room here and online as well towards the end. But I would like to call up our panelists, and we'll sit down and have a little bit of a discussion as we go. So, I think we're going to switch to this one. So, is that one working? Can people online hear? Is there confirmation from someone online?
Yeah, it's all good.
Yep, good. Excellent. All right, so thanks. So I'm joined here now by a few people. We've got a few little questions to run through with them to discuss some of this Antarctic-related science and how we communicate that science and things. Of course, we've already heard from Laura, so we know her. Laura, is there anything about yourself you'd like to say that I didn't say in the introduction earlier? No. Good. Okay. So Laura's been introduced. We're also joined by Alix Post, who is from Geoscience Australia, and then Will Grant at the end from the Australian National Centre for the Public Awareness of Science. Will has first-hand experience of one of these ocean drilling expeditions now as well. We were out a year and a half or so ago on the Japanese scientific drilling vessel, drilling into the earthquake fault from the 2011 earthquake, which actually happened today, 15 years ago. That was a coincidence I didn't think of before. And Alix has a big history in the Antarctic margin work as well. But I'm going to hand you this microphone. We've only got this little one, but I'm going to let you introduce yourselves quickly about what you do and that kind of thing before we switch to some discussion.
Thanks, Ron, and great to be here today. I was thinking as I sat here that my very first research voyage as a PhD student was actually a collaboration between what was the predecessor for Geoscience Australia, so an Australian team joined by an Italian team. Laura wasn't on the voyage itself, but she was very much involved in planning that voyage, and that was way back in 2000 that I had that experience. And yeah, just has really, that was kind of the pinnacle that kind of led me down this track of doing marine geoscience, and particularly focused on Antarctic geoscience. And yeah, just that collaboration across cultures was just, one of the best experiences at that time.
Thanks, Alix. Thanks, Ron. As Ron said, I'm Will. I'm from the Centre for Public Awareness of Science here at ANU. And I'm a science communication researcher, so I look at how science is communicated and connected with different audiences that can use science. And looking in particular at the places where perhaps science runs into barriers, where good ideas don't necessarily connect with the people that can use them, and how we as sociologists of science, but the rest of the scientific and governance landscape can do things to help. And I've just got to say, as Ron said, sailing on the Chiku previously, I think that ocean discovery projects, like Laura mentioned or Ron said before, are a key moment of international collaboration between different scientific groups. And not only can we deliver great results for the world, but we can actually draw and learn from our collaborators and build a better world together. So I really want to highlight that. Thank you.
Thanks. So yeah, so the first sort of discussion here, we've seen, and Laura talked about it in her presentation, the difficulties of doing science in Antarctica. You said on that voyage just now there was places you couldn't go because there was too much sea ice and that kind of thing. But I guess the challenges are much bigger than that. So it's one of the most difficult places to study. Many of the processes remain poorly understood. So it'd be great to hear from each of you what you sort of think. What are your biggest worry about Antarctica? And things that we don't understand yet well enough, and what processes or uncertainties keep Antarctic scientists awake at night. So Laura, I'll let you go first on this one.
I sleep at night. So I'm not I enjoy doing science. It's great, and but I think one of the key things to what we still don't know is the physics of how the mechanism. I mean, how this mechanism work really, indeed, because we have lots of models and simulations, but we don't have enough constraint, enough data to know how the ice sheet and the ocean interact in these ice cavities, because they are very difficult to be assessed. We do use autonomous vehicle, ROV, and we try to launch some of the probes within the cracks and some clues, but it's really unexplored, unknown region, and it's changing all the time. We have ice cavities with warm water, and we have very cold cavities, and we do have sea ice, which is preventing the warm cavities to transition into into cold cavities, but we don't really know what happened there. So that's the future. We should work together, geologists, biologists, sociologists, atmospheric science, everyone should get together to understand how the physics works in the real world.
So most of my research has focused on seafloor, understanding the seafloor environment from bathymetry surveys primarily, and then using that data to understand how those different environments support seafloor ecosystems. We know very little about the seafloor. We've mapped in detail less than 30% of the seafloor around Antarctica. So there's a lot of areas where we actually have no idea what water depth is, and that's really significant for understanding where these ocean currents are actually able to interact with the ice sheet. It's also really significant for understanding where different communities of seafloor organisms are going to exist. So we know maybe 30% of the seafloor bathymetry, but when it comes to actually knowing what species are existing on the seafloor, we know even less. It's from, tiny little pockets where we might have been able to put a seafloor camera down or collect some organisms. But even though we know so little, we actually know that the Antarctic seafloor is incredibly diverse. There's at least 20,000 species on the Antarctic seafloor, and around half of those are found nowhere else. So it's incredibly important to understand how these environments are changing and how those seafloor communities are therefore impacted. But without the information, it's really hard to know whether what we're seeing is actually already a modified community or how they will change into the future.
I don't think I worry about Antarctica very much. Maybe I should worry a little bit more in Antarctica's trajectory. The thing that I worry in this sort of world is public good research receiving less funding than we might hope. I think it's clear from Laura's work here, this can only be done when we have commitments from a range of countries around the world to get down to some of the most challenging places to do research in the world. And largely, this is a public good. This is something that scientists are doing to tell us more about our planet's past and our potential futures, to reduce those uncertainties. And we're moving into a world where perhaps less public good research is being funded. Now, I'm not against research for impact. I think that's an important thing. But I think we at the sciences should also find ways where we can argue for doing public good research and doing the investment that is required to deliver that. So I hope that in the future, we continue here in Australia, Italy, other countries around the world, we continue to invest in understanding our planet's past and future for the sheer importance of knowing world we live on, rather than just being for can we extract resources or can we get direct impact from it. So that's what I worry about.
Thank you all. There's nothing keeps you awake at night, Alex.
Much
Science
used
is,
to.
oh, sure. So I guess coming back a bit to the theme of Laura's presentation is about the the Antarctic research, the Antarctic science. And a lot of that effort is focused on reconstructing how ice sheets have behaved in the past, during times when the temperatures are maybe on at levels that we're on trajectories to reach now. So when you look at these ancient records, do you see analogues for the climate conditions we're moving towards today? Or is there sort of modern situation fundamentally different somehow to those times in millions of years, up to millions of years in the past? I think probably that's a good one for you to start with as well, Laura.
Yes, I mean there are analogs, but the world is evolving. It's always different. So yesterday is different than today. It's different from tomorrow, because the landscape is always shaped by atmosphere, the ocean, and the plates are moving, and so everything is different, and the orbitals. So what we should be care of is understanding how the process works. So we know how much what we expect from feedbacks. So to estimate the rate of change, we need a very good knowledge about the basics. So how the process works. So I think looking at the past and teach us how much sensitive is a gigantic ice sheet to an ocean current, which is below above 1 degree centigrade for 200 years. So have numbers. Try to do an experiment, natural experiment. We should look at how the nature works now to understand the size, the impact of the changes which are facing now and we will see in the future.
I think the fundamental difference of today is that we're accelerating climate change at a rate that we've never seen before. And so while past records, as Laura has said, are really fundamental for understanding how those processes interact, we might be already past some of the tipping points and not realize it because that system takes time to adjust. So yeah, I think obviously we do need those past records, that can help inform our models so that we can understand those processes. But yeah, there are also a lot of unknowns. So it's probably more what keeps me awake at night.
Well, I guess mine would be a question here. Back to Laura again, is how can we see those tipping points and things like that? I mean, that's from an outsider. Of course, we can see, the planet was X degrees warmer in the past, and you can see an environment inferred from the records. But can you see those moments of dramatic change? Can you see where systems change into one thing from another? Because that's what I always wonder about these things. I love that we can learn from history or prehistory to understand the present. Can we see those moments of change really well?
But we do see changes. We do see these West Antarctica sheet melting and accelerating the melt. And we do see the Greenland basically changing a lot. And so there is a large discussion about the definition of tipping point now in the scientific community. So what that means, what is a tipping point? What do you mean? It's a threshold. It's a no return status, but for how long?
Yeah.
So first of all, we should define a tipping point, and then we can discuss are we going beyond or still in a kind of pre-status of. I don't know how to answer really, because as I say, there is a big community speaking about this, but we do see changes for sure. We do see increase of catastrophic events, which is impacting more and more. For example, in Trieste, where I live, Venice is another example, but Trieste is also very close to the sea level. So when we have strong winds coming from sea toward land, we have high tides, we have a storm. Most of our square are when the buildings are flooded. Happens once every 2-3 years in the past. Now it's happening more and more frequently. So we have twice a year. And so because the sea level is rising, so when you have this combination of factors together, you have flood. And so that would be more and more frequent. So are we crossing a threshold? I don't know, but for sure we are accelerating. I'd say we are, yeah, definitely changing the climate.
I guess that flows nicely into the next sort of discussion point, which is around communicating the science. This complex science, science that's sometimes often contested, the challenge of misinformation, denial. When we're talking about these these observations, the community can see that these flooding of the square happens more and more frequently. So from a science communication perspective, how do researchers balance the excitement of discovery with the seriousness of these implications? Laura, you said at the start, I love being a scientist, I love doing my science, but that aspect of communicating that science to make the impact. And maybe for this one, Will, I'll switch to you first. As we've got two expert Antarctic scientists and someone looking from the outside as a communicator. So I'll let you add some words first.
Yeah, sure. I mean, I am really keen to hear how individual scientists do think about communicating the excitement of their work. And this is always going to be a challenge for scientists. I did speak to someone, ethics says I shouldn't say on which project, but who they were staying with their friends and family once, and they got an alert for an earthquake. And as an earthquake researcher, one of their instincts was, oh, that's really interesting. Potentially this will give us new data. It'll be interesting to see what happens. Of course, the human instinct as well as it's going to be a horrific event for the people that are involved. We scientists do look at the world from an abstract position. We remove ourselves from some of the day-to-day concerns to understand the world. And that is exciting. I think that's a thing that all of us learning more about the world, whatever aspect of the world, that's a thing that we do need to keep as part of our jobs. When we are talking to other colleagues in the world, talking to a wider audience out there, talking to school children, excitement is a big part of science. It's not the only part. But I think as well, we have to temper that with, okay, how does my work in this world lead to impacts that improve people's lives? Now, sometimes that's about that public good thing that I said before, that knowing more about our world and our universe, people like that. People actually do. People really, most people out there are interested to hear scientists telling us more about the universe out there, about the world that we live on. So we have to have that. But I think there is a balance between showing the world that we are helping to deliver impacts for them, as well as saying this is actually, it's a joy that society has funded us to go and do these amazing things to tell us about the world.
Yeah, really well said. I was reflecting on this. I went to a science comedy night a couple of years ago, and some of the topics that were being addressed were, very much along lines of climate change and environmental impacts. And I thought, gosh, how are they going to turn this into comedy? They're such serious conversations, really. What really struck me in that was, the way that the presenters were able to engage that audience through comedy, where they were not making fun of the science or making light of the science, but just providing that window into more of who they were and their experience. So making fun of themselves, which is, very Australian thing to do. And yeah, I think that really helped to build trust with that audience, so that when they were then giving those harder messages, the audience was more receptive to that, because they kind of built that trust by revealing a bit of themselves. So I think that authenticity and just being willing to, share the story of, how that science has shaped you as a person as well, really helped to then communicate those scientific findings.
Yeah, I think a way to talk to the public, to the community, to vehicle a bit more our messages, to actually show the impact of what could happen, and give a, rather than a catastrophic view about the future and be depressed. My way is generally to to discuss about adaptation. So the world is changing. Our activity sometimes is hard to stop. We have big communities, so even though some countries are more conscious, other countries are not, so there is a lot of political issues. So let's think about adaptation. Are we ready to adapt? What would be the cost of adaptation if we act now and we are too late? So in this way, I think the community is more like keen to follow your way of thinking and accept the scientific contribution, your knowledge from science, because it's applied to their living life and the future generations. So that's my approach to me.
Thanks. Some great perspectives there. And I think that probably also leads nicely into the next little topic we had around the collaboration. And, we all know that these big science programs rely on that collaboration between the scientists. And I guess it's just a chance to maybe for you to reflect on how do these different levels of expertise, these different discipline expertise, the perspective shape the way that discoveries happen on board these expeditions, or when you're in Antarctica doing the science, out on a ship doing it. So have you got any sort of stories about what might happen to bring on these discoveries and these big collaborative things, and maybe touching a little bit on the challenges of that as well, in terms of the cultural differences, the geopolitical challenges, if there's anything to add on those points as well. Now, I'll start with you this time.
Yeah, what I enjoy most about going to sea and going on a voyage is just you're bringing along that multidisciplinary team, different perspectives on the data that you're collecting. And I think, a lot of the voyages I've done have been collecting sediment cores. And so that starts with the geophysics of, understanding what that seafloor environment is and what the sedimentary processes below the seafloor have been, so that you have some sort of idea of, whether that's the target that you want to be collecting a sediment core from. Is it likely to give you the record that you're needing to understand the questions that you have? But then when that core comes on board, just the flurry of activity of all the different disciplines taking their samples, you'll have the biostratigraphers taking samples to get an understanding of how old that core is. Then you have the sedimentologists coming in and describing that core, different structures in it, the different colours, the different composition of it. And you're building up layer by layer this really rich interpretation of how that sediment got there, what the processes were, what it means about how that environment and climate was changing. And so I just love seeing all those different disciplines across the microfossil community, and then the physical properties of looking at changes in the rock composition and other particles coming together to, it's like reading a crime novel where you're trying to work out exactly what's happened over the course of that record.
I agree. I think seeing interdisciplinary labs work together is wonderful. I think what I would say on this is that we in the sciences, we have this high bar for discovery. Like discovery means we go out and do a big voyage, and there's the number one thing is the nature paper or the science paper at the end. And that's very, universities love it, our governments love it, that's great. You get the high profile thing. But I think the other way we can also think about discovery is at the much smaller level, where the sedimentologists are working with the physical properties group, or might be working with other disciplines. And there can be a moment of discovery between two researchers when, you hadn't known something before, and then you're working across a disciplinary boundary. And then suddenly there's new knowledge generated between you. Maybe that's just enough for, those two researchers to understand something. Maybe it's something that might lead to new insights further down the track. But I think we should build ourselves in this idea that little bits of discovery happen all the time. And that is a big thing for us, that we should be funding our researchers to go and collaborate with other disciplines, because then they will be better researchers when they come home. They'll be better able to collaborate with other people that have lots of different ideas. Part of the reason we do this is to train our researchers to be better researchers here, and that's by collaborating with people in different disciplines in different countries.
Yeah, I totally agree with everything being said so far. But I the last example is this voyage I was just with Linda and the others. And there were a whole bunch of disciplines, biologists from micro to macro, and physical oceanographer, geologist, sedimentologist, petrographer, and geophysicist. So basically a whole bunch of disciplines represented. And we did make discoveries, unexpected. I cannot spoil too much, but it was very lovely because we collected already a bunch of geophysical and sedimentological sediment, but the biologists were very frustrated because we didn't go to the continental shelf, which is where the animals are living. So we wanted to get something for them before we go back. So we went to this region, which is the Ebor Glacier region, which is nobody knows about this. It's basically an unexplored place, but that's the only place where you can go to the continental shelf. There will not see ice. So let's go there the last 2 weeks before we go back. So the biologists go back. Something. So we did. And we discovered this region. That was an incredible place. We collect a bunch of sea stars and octopus and a bunch of things, but also two very good cores. And we did map the seabed. And it's a very interesting place where we need to go back and collect some data because it will tell us a lot about the Antarctic wildlife. So yes, we do discover something we would like to learn all the time.
Some accidental science from keeping some people happy. Look, just to wrap up this sort of part of the discussion, so we can take some questions. We know that these big Antarctic projects, initiatives, they rely heavily on the shared infrastructure, the shared logistics, the shared data. The same goes for these scientific drilling programs around the world with the big ships to run those, which are all very expensive. But I think we'd be reasonably confident those programs have been quite successful. And I guess the last sort of question here is, what lessons do you think other areas of global research could learn from the way Antarctic science operations happen? And I don't want to take that question first. Any thoughts? Not first.
Yeah.
Yeah.
Yeah, I mean, Antarctic science is the most collaborative science that I've ever been involved in, because you can't do it by yourself. No single researcher can support themselves to do the research. You need to form a consortium of researchers, and often across international boundaries. We've got a icebreaker, and we've got single blue water vessel, the Investigator. It's ice strengthened, but it can't go into the ice. Our icebreaker is an amazing combination of capabilities, but it also needs to supply our research stations, so it's not available for science all the time. So, there's only so many opportunities that a single country even has to undertake that research. And so through collaboration, we obviously have a lot more access to different parts of Antarctica, different capabilities, and also that different knowledge and understanding that those researchers have built from being involved in research in different parts of the Antarctic margin to where maybe the Australians have had that opportunity. And so I think for other sciences, I just encourage people to find those opportunities for collaboration, because it really does make that science and that understanding so much richer.
So, lessons for other science. I mean, I think you are unique in the sense that Antarctica is a unique place in the world, politically, certainly, but also climate-wise, it tells us different things. Looking at the other big international collaborative pieces of science, like the Large Hadron Collider or the International Thermonuclear Reactor or something like that, they're constrained in different sorts of ways that governments want outcomes, or the bit of kit has to be located somewhere, so governments will fight for those kind of things. I think the key lesson here is that big things only happen in collaboration. So we have to, in some sense, share the winnings, share the costs, share the advantages. But I think if we're thinking about impact for the world, then we're on a pathway where we can think, okay, how can any of this help the world? If we think we have the world in the back of our mind, then we're on a pathway to good collaboration. Yeah.
Yeah, one thing I can add is to learn the lesson from SCAR, the Scientific Committee for Antarctic Research, which is a place where all nations meet every 2 years and take decisions, but discuss also about science and share results, but also the need to go somewhere and together. COMNAP, which is the consortium of Antarctic logistics, Antarctic problem logistics, is also attached to SCAR. So these two entities are really key for building a very good international collaboration in terms of logistics and science. So this is the recipe actually to do something similar somewhere else in other regions, like thinking about the Atlantic or the Mediterranean region or other regions where maybe scientific teams are more fragmented, that they don't have a forum where they can actually share these ideas. So yeah, I think SCAR is a very good example.
So thank you, panel. So we will take a few minutes now, 5 minutes or so, maybe just to take some questions from the room and online. And I think Sarah over here is keeping an eye online. And we'll kind of direct those questions, but if a question comes and you think you've got an answer, panel, then please put your hand up. Say, yes, I can take that one. We do only have this one microphone, so I might have to, well, maybe I can run it to anybody in the room who has a question. Otherwise I could repeat the question. So would anybody in the room like to ask a question?
We're halfway through the United Nations International Decade of Ocean Science, so we've got 5 years left to take the opportunity presented by that. Do you think the Antarctic research community is in a position to benefit from that by 2030?
I don't know if I can answer, but we also have the International Polar Year Initiative, which is 2030-2032, which is coming. So I think that would be a good ramping up phase for all of us to take the opportunity to design very big scientific projects together. So I think that the moment is now, and looking at 2030, 2032 is a long time enough to actually build something significant.
I guess another some big international focus at the moment for the Antarctic research is a program called InSync, which I'm not sure if it's directly tied to the Ocean Decade, but it's all about trying to get synchronous measurements across Antarctica. So I think, you know, having these sort of key kind of events can help to mobilise the community and bring them together to focus on those aspects. So I think they can be really, really significant in sort of, you know, providing a kind of time frame like the International Polar Year to really get the community thinking, what can we do together that's going to make more impact than just our individual programs can.
Well, the only thing I'd add to that is when you say, Alex, the community, absolutely, it's you know, communities of researchers, and remembering there's a bunch of different in there, but Grant, as you know, Questicon, obviously, that's part of the community as well. And as you synchronize measurements across Antarctica, I don't know what that project is, but that is also a great moment to bring in the rest of the community, say, hey, there's a reason we're doing these kinds of things. They can be moments of focus that can draw people into the community. And I do know geoscience is very much thinking about how you can get people into the community.
Thanks. Perhaps there's a natural progression from ocean decade to polar decade or something. I think that may have been talked about. Behind you. Oh, I missed it. Did anyone catch that comment?
There was a hand down the comment.
Yes, well, there you go. Sarah's made the comment that maybe a UN polar decade in the near future would be good. So we do have a question online. We're good to go to that one. Yeah. So
thank you. I'll start with this one. We are.
Hang on, let me. that as well. So.
We are a group of year 11 and 12 students watching from water at Kildare Catholic College, and we were wondering about the implications of loss of sea ice of specific endemic species such as emperor penguins. What does the future look like for these species?
Anyone? Yeah. Anyone else in the room?
Yeah, so the loss of Antarctic sea ice is one of the most concerning things that we've seen in recent years. And it really, is, it's fundamental habitat for emperor penguins. It's where they raise their chicks, and those chicks don't have waterproof feathers for about 9 months. So they actually need a stable platform to raise these chicks until they're about 9 months old. And there's been some really disturbing research that's shown that, emperor penguins are having to move or not having successful breeding seasons. Finding, I don't know how we help them adapt to that, but they are a resilient species that have been around for thousands, not millennia. They have been moving to different breeding sites, and so they have that adaptability. But it's hard to really know what the future holds in the longer term for those species, unfortunately.
I get that. That's a really good question in terms of the consequences of some of these changes, and they come up and they surprise us, and maybe we don't have the answers immediately. Another one that I've remember hearing recently is the potential that these nodules of critical minerals, rare earth elements on the seafloor could be producing oxygen in the ocean. Now that's a little bit of a controversial thing in some people's minds, but these things pop up and we think, oh, hang on a minute, we haven't thought about that. But it really helps us focus our efforts and focus where we want to go. And I think that school group there you've just seen, I think you can be reassured there are scientists who've jumped on that problem, recognizing that the sea ice is it's really sensitive to these changes, and there are people jumped on that problem and they're really looking to solve it. We did have a question over here. Maybe I'll go here and then we'll go online for another one.
Good morning, and thank you for the presentation and the discussion. My name is Vitaliano Gallardo. I'm ambassador of Peru. I usually participate as delegate in the Camara meetings here in Poland. And then I'm trying to connect dots between science and some of those aspects I didn't realize the presentation. There is a mention that it is still need to continue to do research. And in doing that research, there are different aspects, like the warm water, how that penetrating the ice shell, but also what is the evolving process of the species living in this area, and what could be the conservancy measures that we need to take. But science requires two things, from my experience: certain convergence of scientific point of views, because there are a lot of discussions about if we are doing it full in parameters, consensus in the methodology we use, or even the application of certain techniques. That is the reason there is not full agreement in the scientific discussions in Camara related with the data is showing to adopt certain decisions on maritime reserve areas. Then there seems to be there is a problem of discussions in science itself to be acceptable for some different other scientific communities. The second element is budget. Science requires budget, and budget for equipment, budget for the work done by the scientific itself. Then those aspects in connection with the requirement of science, what is required for the scientific people in relation with the political diplomatic actors. This is one of the first questions. The second one is something that it is related, because it has been pointed out that we need to interconnect. It's true that we need to know how the seafloor, how do the species react, how the ice itself. but it seems that if you connected some elements, you are going to aggregate and complement and make a more comprehensive elements of analyzing. When there is a connection between the mountain and the sea level, you start to see that it's really huge, the amount of connections. What is the way to precise the connections, and at the same time, what is the level to expand these connections? And the last element is obviously the diplomatic effects. We have been evolving the process of what is the Antarctic system working now. There is a future review that it's going to happen. But at the same time, there are elements very concrete for the people living in the Pacific. What that means, diplomatically speaking, 1, 2, 3 meters of the rise of the sea level. It's going to disappear some states. Currently, there are discussions about what could be the effects protecting the territory underwater when that happens in some countries. Thank you.
Yeah. Well.
About the question about the protocols when you look at the environment, how we study it, how we measure it, different kind of approach. That's true. And this is one of the things that STAR is also trying to address. For example, there is an action group which is called Istituto, and it's dealing with the calibration of proxy and pilot proxy. So it's a really practical action group which wants to know what are the protocols that are now adopted to actually measure the water temperature, the salinity, the seabed roughness. So all these things that are obvious, but they're measuring sometimes in different way, but different things, biologists and geologists and so forth. This action group has a lifespan of 4 years. In 4 years, they come up with a report, information shared and discussed, and this is one of the potential step forward in Antarctic science. And for what the policy can do to help our scientists to better work together and make another step forward, I guess that what you can do is to talk to your Antarctic program, and perhaps, for example, one of the things is not use an icebreaker to supply each station, but only for one nation. But maybe you can use an icebreaker supplying the Italian station, the US station, the Korean station, the Australian station, and then we all together use another icebreaker to do science together. Because in this way you optimize the logistics with one ship, which has different needs, a different time frame, different kind of items that you have to bring on board. And we optimize the use of the icebreaker only for scientific purposes. So this is something that the policy can help us to actually improve in order to have better science, better organized science.
You know what to add? Right, look, I have seen we've come to the end of our time, but maybe we'll take one more online question on it. I'm in this difficult position now that time's up, but I'm sure there's so many more burning questions. People in the room, I guess you have a chance to approach people afterwards, but maybe we could go to one more online question.
This question is from Ernie Martin, and he asks, can the intensity and frequency of 21st century weather events be compared with historic events in the time periods shown in this seminar?
There are extreme events in the past, and I show this map what was happening 15,000 years ago. In 300 years, you have 20 meters of sea level rise. So yes, I mean, there might be analogs. I mean, there might be something happened in the past, but yeah, again, the message I'm trying to deliver is that we don't really know what happened, how much. What was the triggering factor? What were the feedbacks? So that's That's all I can say. If you want to add anything else.
Okay. Look, we might be forced then to draw it to a close because we've reached the sort of the time limit. Yeah, thank you to our panelists here. I'm sure, Marco, would you like to say a few closing words, something at the end?
I didn't prepare any. So
Didn't prepare anything? He doesn't have, okay, all right. So look, I will draw it to a close then. Thank you everybody for attending here in the room and also online. This is probably the fullest seminar room we've seen here for quite some time. And I think that's really a reflection of that collaboration, that connection. There's a bit of an Australia-Italy focus here, but we've got people from other countries here as well. And it's really good to have that connection, and it really just highlights that for a lot of this advance and in understanding, we've got to connect the people. I'm surprised every day that when you put two people together, they go, oh, hang on, yeah, we know we've got some commonalities, some things that we can work on. And I think we really need to encourage that. And I think this kind of thing has hopefully helped a little bit of connection like that. And yeah, let's see where the future takes us. So again, thank you everyone for attending. Thank you to the people who've helped. I know the two, Jerry and Sarah from ICEDS have been great in getting set up. Adele's been really helpful getting the tech set up as well. Liz has helped us with the bit of the logistics here this morning. And of course, Sarah Kasovich online, who couldn't be here today. I know she desperately wants to be here today. Thanks, Sarah. Yeah, hopefully we've done it justice for you. So yeah, thanks again, everyone. And yeah, hang around and have a chat if you like. Thanks.